In this lecture, we'll study about the scalar and the vector potential. Now, before continuing our discussion with the scalar and vector potential, let me state some facts about the Maxwell equations. Okay. Please see that Maxwell equations are all total of 4 equations. So we have 4 Maxwell equations. Agreed? And we have a total of 6 unknowns. We have total of how many unknowns? 6 unknowns. The 6 unknowns are the 3 components of electric vector and the 3 components of magnetic vector. So the question is there a way I can reduce the number of unknown equations to 2 and the number of unknown variables to 4? Is there a way? The answer turns out to be yes. So why are we doing this? To make our life easier. Because instead of solving 4 equations with 6 unknowns, it is better to solve 2 equations with the 4 unknowns. But what should be the nature of these 2 equations? These 2 equations should keep in itself or should contain all the informations that are there in the 4 equations of Maxwell equations. Agreed? So these 2 equations must have all the information of Maxwell equation, and these 4 unknowns should be such that we can find all the 6 components of electric and magnetic field using the 4 unknowns. So we'll see what are these 2 equations and what are the 4 unknowns as we go forward. Now, before continuing with scalar and vector potential, let me tell you something about Poisson's and Laplace equation. Agreed? So you all remember the Gauss famous equation? Okay, that is del dot E is equals to rho by epsilon naught. This is the differential form of Gauss equation. Now, we all know that electric field has a potential, and electric field is related to that potential through the equation E is equals to gradient of V. V is the potential of electric field. Now, this equation can be written in terms of potential. So this will become del square V is equals to rho by epsilon naught. So I have ignored the minus sign. Okay, just ignore the minus sign. So consider just imagine you take only the positive one. Now, what is the importance of this equation? You see, every second order or every differential equation are the fundamental equations. They carry all the information. For example, you remember your classical formula, force is equals to mass into acceleration. Now this formula is nothing but a second order differential equation, because your force can be written as the second order mass multiplied with second order time derivative of position. Okay, and on the right hand side you can give the information what type of acceleration you are using, whether you are using g or whatever. Similarly, you can change this equation according to the environment given. So if you have an environment where you need to add something here, you can do that, and a lot of things can be done. But this is the most fundamental equation that contains all the classical mechanics inside it. This is the gist of Newton's formula, force is equals to mass into acceleration. Everything, even the equation of motions and everything is inside this particular formula. Similarly, this Poisson's equation is the most basic equation for electrostatics. Why electrostatics? Because see, you see, Gauss theorem is usually for electrostatics, where you have static charges distribution. So there are some charge distribution on space, and for this particular charge distribution in space, you calculate the electric field at a particular point. This is what you do using electrostatic, and for this you use either Coulomb's law, or you can say you can even use the Gauss law to do the same. So Poisson's equation can be converted into a Laplace. So consider a space where rho equals to 0. Then for that space del square V is 0. This contains the information of what the electric field should be in a space where there is no charge. Now you would say, if there is no charge in a space, obviously electric field is 0. No, there are other cases where there is no charge in the space but electric field is not 0. A simple example is, consider two capacitors. This capacitor is positively charged and this capacitor is negatively charged. Now the gap between these two capacitor is empty. There are no charge between these two capacitors in this gap, but you know that the electric field in this gap is this. We all know that electric, so it means even though there is a gap there, but electric field still exists even though there is no charge in this gap. So in this type of problems, to find the nature of electric field, you solve this Laplace equation and you find V. So once you find V, you can easily find electric field. Now how can I use this equation? Wait, you can use this equation directly, but you need to give the boundary conditions. The boundary conditions will specify the environment you are talking of. For example, in this environment, the boundary condition is that the, so consider this is x equals to 0 and this is x equals to a. So the boundary condition is that the potential at x equals to 0 and the potential at x equals to a, okay, they should be same but with a minus sign. Similarly, there are various other conditions, various other environment where the charge may not exist but electric field may exist. In those cases, you use Laplace equation. And the environment where you have a distribution of charge and you want to find the electric field, you use Poisson's equation. So what I want to say is that Poisson's equation is the most fundamental equations of the electrostatic. So it is more fundamental than the Gauss law because Poisson's equation is a second order differential equation. Now just keep this in mind, we'll use it further. Okay, now let us turn our attention to scalar and vector potential. So a little bit of change of track. So we all know that electric field has a potential related to it, and that is the electric potential, and the electric field and the electric potential are related through a gradient. So electric field is gradient of V. Now the question is, can a magnetic field have a potential like an electric field? So what will, if there is a potential related to magnetic field, so what will be the potential like? So can I say if I assume the potential of magnetic field is A, so can I write B is equals to gradient of A? So can I just write B is equals to minus of gradient of A just to make it analogous to the potential and the electric field relation? The answer is no, you cannot do this because this will not satisfy this equation. That's the problem. So how to go about solving this problem? So let us think a bit.